The semiconductors. Semiconductors have properties between metals and nonmetals. Metals conduct electricity, nonmetals don't. Semiconductors kind of do, right? Band theory is one way of understanding how they do this. It's a more comprehensive model for metallic and covalent solids that grew out of molecular orbital theory. And we're just going to keep in generalizations. So the idea here is that the atomic orbitals of atoms within the crystal solid combine and are delocalized over the entire crystal. So in some sense, the crystal is like a very large molecule. When you have those orbitals forming, remember molecular orbital theory, you combine two orbitals, you get one that's lower in energy and one that's higher, right? You get a bonding orbital and an anti-bonding orbital. If you've got a lot of atoms doing this and a lot of orbitals combining, what happens is the difference in energy between the anti-bonding and the bonding becomes less and less and less. So here we have an example looking at lithium. So here's one lithium atom, and there's the orbital with its valence electron in it. If we have two lithium atoms, and they're going to combine their orbitals into molecular orbitals, one will be higher and one will be lower. You get 3, I don't know how to explain that one. 4, now you've got 2 that are lower and 2 that are higher. And as you keep adding more and more and more, the difference between these becomes less and less. And it essentially fuses into what we think of as a band. Instead of a molecular orbital, it's like a band. So we've got empty orbitals. The anti-bonding orbitals are going to be empty, and the occupied orbitals are going to be the bonding orbitals. So we call this the valence band. That's where the valence electrons are. This is the conduction band. So electrons can be free to move when they move from that valence band into the conduction band. So let's go back to this for a minute. The electrons are all going to be here. These are occupied orbitals, the valence band. All these orbitals are full. So these electrons can't really move from one orbital to the next, or from one side of the substance to the other. Up here are empty orbitals. If one of these electrons can jump up here, it could move. Okay, I think of this valence band as being a highway in gridlock, right? There's a traffic jam and nothing's moving, right? You can't go anywhere. The empty orbitals, the conduction band, this is the shoulder of the highway. You're not supposed to drive on the shoulder, right? So, people are being good and they're staying here on the highway where they're supposed to be. They're not moving. If you go over there onto the shoulder, though, you could just zip past the traffic jam. So why don't you? Because if you get caught, bad stuff happens, right? Some people care, some people don't. Well, I think I skipped something. Yeah. So the valence band is the congested highway. The conduction band is the shoulder. It's empty, but this is higher energy. That's that penalty you have to pay if you get caught over there, right? You have to be willing to pay that. So in metals, there's actually no gap between the valence and the conduction band. So you can go over onto the shoulder and zip along, and nobody's going to say anything. You're not going to get into trouble. So metals conduct electricity easily because the electrons can easily move into the conduction band and zip along. And that also explains their thermal conductivity, because those electrons have kinetic energy. And as they are able to move in that conduction band, they can transport their kinetic energy, which is related to the thermal energy, from one side of the crystal lattice to the other. So here we have illustration of the bands in a conductor. Here's the valence band, the conduction band. There's no energy gap here. So an electron can easily just move up here. It doesn't require any extra energy. And now this is mostly empty, and so it can move around. In an insulator, like most nonmetals, most molecular substances, there's a big energy gap. If you want to jump up into that conduction band and be able to move, there's a huge energy penalty, and so they don't do it. And then we have semiconductors. There's a small energy gap. And so they will conduct a little bit, because some of the electrons will have enough energy to move up into the conduction band and move around, but not very many. And so it conducts electricity, but only a little bit. The conductivity of the semiconductor is going to change based on the temperature. Because if you heat up the semiconductor, what does that do to the average kinetic energy of the electrons? It goes up. More of them are going to have enough energy to get into the conduction band. So you heat a semiconductor up, its conductivity increases. Semiconductors can be used as temperature sensors, because you can measure their conductivity and it will change when the temperature changes.
And also the switches, like you get like an electrical charge to one side of the like a transistor, and it heats it up and it allows electricity to flow.
Yeah, this is the basis of all modern electronics, transistors. So this difference in energy is called a band gap. And so if there's a large band gap, it won't conduct. If there's a little band gap, it will conduct a little bit. And if there's no band gap, it conducts well. As you go down a column of elements, that band gap decreases. And we know that as you go down a column, metallic character increases, right? Metals conduct electricity. So here we're looking at group 4. Carbon is a nonmetal. Silicon and germanium are semimetals. Tin and lead are metals. And we see that the band gap decreases as you go down. And so the conductivity is going to increase. We can control the conductivity of semiconductors by adding impurities to them. This is called doping. Yeah, so a doped semiconductor. It's got small amounts of impurities, and there's two different types. There's an N-type and a P-type. One makes holes in the conduction band, and one makes holes in the valence band. So an N-type. N-type contains extra electrons, and those extra electrons, because the valence band is full, any extra electrons have to go into the conduction band, and they're going to be up there all the time, so they're always going to be mobile. So what we can do is we can take something like silicon. Silicon has 4 valence electrons, and we can add a little bit of phosphorus into it. Phosphorus has 5 valence electrons. Now there's going to be some extra electrons that aren't going to fit in the valence band, and so they will go into the conduction band and increase the electrical conductivity. So that's an N-type. The charge carriers are the negatively charged electrons. The P-type is where we're making essentially holes in the valence band. So here we could dope silicon with something that has fewer valence electrons like gallium. And so now we have fewer electrons, so there are going to be some holes in the valence band. Those holes can move because an electron can move into the hole, and then the hole is behind it. So it's like you had a gridlock situation, and you went through and pulled out every 15th car. And so you pull out a car, what happens? Well, the car behind the hole moves up. Now there's a hole behind him. The car behind him moves up. Right? So now you can get conduction in the valence band. These are called P-type because we think of it as a positive charge moving. So silicon chips have these PN junctions. And so we get these can act as diodes, which allow current to flow in one direction. They can act as amplifiers, taking a small current and making it into a larger one. And this is a whole different subject, right? But it has to do with essentially molecular orbital theory in these conduction and valence bands. Okay, which element would you dope into germanium to create a P-type semiconductor? So P-type, P is for positive. So we've got a positive hole that's moving, right? So if we've got, electrons, I'm just going to make them negatives. Electrons, right? And they're all stuck in this conduction band. I'm sorry, the valence band. There's the valence band, and here's the conduction band. And these guys can't go anywhere because it's full, right? P-type, what we're going to do is we're going to take out some of those electrons, and now they can move. This one can move over here, this one can move over there, and then this essentially is like a positive hole that's moving in the other direction. So what we need here is we need an element that has fewer valence electrons. So silicon has how many? I'm sorry, germanium. We're doing germanium.
4.
Germanium has 4 valence electrons. This has 4. And we've got indium has 3. And tin has how many? 4. And arsenic has 5. So we would want to use indium to make a P-type semiconductor. Because we've got a few indium atoms in here, they only have 3 valence electrons. Every indium atom that's mixed in with your germanium is going to make a hole. Because it's short an electron. What would happen if you used arsenic? It'd be an N-type. Because now what you have is, so you've got these from your pure germanium. Let's get rid of that. And you throw in some arsenic. Well, the arsenic has 5 valence electrons, so every arsenic atom, its extra electron is going to have to go into the conduction band. And they're going to be up there all the time. And so that will conduct. So the answer to this question is indium. Any questions? Yeah.
Tin wouldn't do anything. It wouldn't be a P-type or N-type?
Correct. Tin would not really do anything to the conductivity of germanium because it has the same number of valence electrons.
What if it were something like iodine?
Iodine with 7, that would be an N-type semiconductor because it's got more electrons. Of course, there's a lot of these combinations that probably have been tried but don't actually work very well, but we don't have to worry about that.